All right, in problem 4, part A, it says use Stokes' theorem to compute the circulation of the following fields along any simple closed curve C. Okay, now I just took this wording straight from the textbook, and you'll see it in my math lab as well. When they say use Stokes' theorem to compute the circulation, what they're really saying is to use that theorem that we proved in the last video. Okay, and that says that if the curl of the vector field is equal to 0 throughout some region D, which is open, connected, and simply connected, then you can conclude that the vector field is conservative. And so that then is equivalent to the circulation of the vector field over any simple closed curve to equal 0. Okay, so let's illustrate that with these vector fields. So for our first vector field, f, right, y squared z cubed, comma 2xy z cubed, comma 3x y squared z squared, well, we can easily check that the curl is 0. And the domain of this vector field is all of R3, which is open, connected, and simply connected. And so from the last video, this vector field is conservative on R3, and so the circulation is equal to 0 for all simple closed curves C in R3. All right, that's it. For the second vector field, right, it's equal to the gradient of this function x times the sine of y times e to the z. And put another way, this function is a potential function for our vector field f, and our vector field is conservative. That's really what it means to be conservative, right? Is that it is the gradient of some function. And so if we're conservative, then we know that the circulation is equal to 0 for all simple closed curves C in R3. All right, for the third vector field here. Now I should have included some conditions here on the component functions f, g, and h, but we'll just assume that they're defined over all of R3 and they have derivatives of all orders. Okay, so in other words, they're very nice functions. All right, and so notice that the I component depends only on x. That's what this expression f of x is telling us. And likewise, the j component depends only on y, and the k component depends only on z. So if you take the curl of a vector field of this form, you get the 0 vector, right? For example, the I component here would be the y derivative of h of z. Well, that's 0. Then I'm going to subtract from that the z derivative of g of y, which is also 0. And similar calculations for the j and k components show you that those are both 0. So the curl here is the 0 vector. And by our nice assumptions on these component functions, okay, our vector field f will be defined over all of R3, which is open, connected, and simply connected. And so we know then from the theorem in the last video, the vector field is conservative, and so the circulation is equal to 0 over all simple closed curves C in R3. All right, cool. So now let's go ahead and make a little space and look at part B. So here, you'll notice that the I and the J components, right, these are, of course, familiar to us from our work in sections 15.3 and 4, right? This is that radial field we kept looking at. Now here we have that radial field plus this K component, which is just Z here. Now our job is to show that the curl of this vector field is 0. But the circulation of the field along the unit circle in the xy plane centered at the origin with a counterclockwise orientation is not 0. Okay, and so then the question says, well, why doesn't Stokes' theorem apply in this instance? Well, let's first discuss the curl. So for the I and the j components, the fact that those are both 0 is really immediate, right? For the I component, for example, I'm taking the y derivative of z, well, that's 0, and then I'm going to take the z derivative of this quantity that depends only on x and y, so that's 0. And so that difference for the I component is 0, and likewise for j. Now for the k component, well, I'm looking at the x derivative of this function, x over x squared plus y squared. And then I'm going to look at the y derivative of this function, which is negative y over x squared plus y squared. So if you go back to quiz week 6, problem 2, that's where you were looking at this rotation field, and you were asked to show that del q del x was equal to del p del y. Well, that's exactly what this calculation here is doing. This is just computing the two-dimensional curl. of this vector field. Okay, now the k component of the three-dimensional curl is the two-dimensional curl, so really it just boils down to that same calculation. Okay, so the curl here is 0. So then you might say, all right, great, that means this vector field is conservative. Well, not so quick, right? Let's go ahead and compute the circulation around the unit circle here. Let's see what we get. So we're parameterizing the circle, so it's counterclockwise when I look down on it. So I'll parameterize it as cosine t sine t 0, and t varies from 0 to 2 pi. And here's our derivative vector. And so to compute the circulation integral, we're going to evaluate our vector function f along the circle, and then dot that with the tangent vector. And so to evaluate the vector field along the circle, we're going to set x to cosine, y to sine, and z to 0. Okay, and so note here for these denominators, we get cos squared plus sine squared. That's just 1. So these denominators are both 1. And so I'm going to get negative sine t, and then cosine t, and then 0. All right, and then for the tangent vector, that's just minus sine cosine 0. So these are in fact are the same vector. You dot them and you just get sine squared plus cos squared, and that's just 1 from the Pythagorean identity. So our line integral here has a value of 2 pi. Okay, so what does that say? Well, in particular, since the line integral over this simple closed curve C, right, the unit circle here in the xy plane is not 0, then we can conclude that this vector field, in fact, is not conservative, right? We know from section 15.3 that a vector field is conservative if and only if the line integral over any simple closed curve in the domain is equal to 0. Okay, and that's not the case. We get a non-zero circulation integral here, okay? So we're not conservative. So then you might say, well, then what's, what's going on here? Why doesn't Stokes' theorem apply? Why can't we apply that theorem that we proved in the last video? And the issue here is the domain of f is not simply connected. Okay, so note that this vector field f will be defined everywhere except when these denominators are 0. And that's going to happen when both x and y are 0, but z can be anything. So that's saying, right, that the domain of our vector field is all of R3 excluding the points on the z axis. And this is not simply connected. Why? Well, let's say I have this loop here, this simple closed curve that wraps around the z-axis. And to be simply connected, that means I have to be able to continuously deform this green curve to a point while remaining entirely in my set. And since I'm wrapping around the z-axis, right, no matter how I try to continuously deform this thing, if I'm going to shrink down to a point, there's no way I can do that and remain entirely in my set because of this barrier of the z-axis. So we're not simply connected here. And so that theorem from the last video just simply does not apply. And I make this comment here. Stokes' theorem doesn't apply here since f is not defined along the z-axis, and C encloses the origin, which is on the z-axis, right? So this unit circle here, centered at the origin, it wraps around the z-axis, and so Stokes' theorem is not going to tell us that line integral is going to be 0, even though our curl is 0, and that's again because it just simply doesn't even apply in the first place. Okay, so now the last thing I want to say in this video, this is on the second page of Stokes' theorem worksheet. This is now a complete summary of all of these various conditions on determining, or sorry, of a vector field to be conservative. Okay, so it says here, f is conservative is equivalent to the line integral being path independent, which is then equivalent to the circulation integral to be 0 for every simple closed curve C in the region D. And notice these three equivalent conditions, these are all from section 15.3, and they are just making the assumption that the region D is open and connected. Now, if we also know that D is simply connected, then I can add this condition that the curl of the vector field is 0 to this list. Okay, but as this example shows here in part B, if D is not simply connected, then it is possible for the curl to vanish everywhere in the domain, but nonetheless, the vector field is not conservative. Okay, so if D is not simply connected, then you just have to do more work to determine whether or not the vector field is conservative or not. It could be conservative, but it also could not be, as this example 4b shows. All right, well, that's going to do it for this video. I will see you in question 5 next. Thanks.